My name is Charles Harris. Um, Today I'm going to be presenting a paper for Econ 7217, Economic Analysis of Social Networks. This paper is titled Modeling Dependencies in International Relations Networks. It was published by Peter D. Hoff and Michael D. Ward in Political Analysis in 2004. All right, so first introduction. There's a long-standing tradition of the concept of sovereignty in international relations. Basically, this says that the only important actors on the international stage are nations, and then it simplifies the model. So it discounts the actions of individuals, firms, non-government organizations, etc. But there's increasing evidence that these non-state actors do in fact have significant influence on international events. And so there's widespread recognition also of the interdependence among the salient actors, both countries and non-state actors, but this is typically ignored in empirical analysis because it's difficult. And so in this paper, Hoff and Ward present a regression framework that accounts for these dependencies in valued and binary dyadic IR data. So if you're like me, you don't know what dyadic means. Dyadic just means it's directed between two individuals. It's a directed action, and it's a binary between the two actors. And so there's senders and receivers in these networks. And then additionally, and so some of this had been done before. One of their novel contributions in this paper was to allow for third-order dependence in their model, and they did this with including the inner product of latent variables in their regression model. And so we'll talk more about that later. All right. Here's the model they use. They start with a general linear model, and so here it's a little bit higher dimensionally than I think what we're used to. So here, y is rather than being a vector, is a matrix of dyadic measurements, and so this is often called in other branches of social sciences often called a sociomatrix. And so this is a matrix of measurements such that the ijth entry is the measurement of some relationship from I to j. So this is an n by n matrix, n being the number of actors that we're considering. And then x, rather than being a matrix, is now an array. And so it's an n by r array. Such that x sub ij is then a vector which describes the characteristics of that relationship, that dyad, from I to j. And so in kind of matrix form, we get y equals x beta plus epsilon, which is our error term. You can see in my little graphic just there's directional interactions. We have the observed actions of I on j, as well as the observed actions of j on I in this dyadic data. And so they also incorporate a linear random effects model. So this is called either a socio model or a round robin model. I'm not sure if round robin is the term used in Taiwan, but it just means that everybody plays everyone else. If you had a round robin tournament, each team would play every other team. But anyway, in this model, they assume that the errors are normal, and then the covariance is exchangeable under the permutation of the indices I and j. So the ij correlation and the ji correlation are the same. And the further they decompose these effects into sender, receiver, and dyadic components, so that's a sub I, b sub j, and then gamma sub ij. And so those sum together in our error term here. So E sub ij equals ai plus bj plus gamma ij. And so when we look at the distribution of these, they're distributed about 0 with the following covariance matrices, and we can see that sigma squared sub a is the common sender covariance, and then the sigma b squared is common receiver, and then captured in this rho term, so rho sigma gamma squared is the reciprocity between the actors. Okay, so these relationships define these following moments of the variance and covariance elements. All right, and so they then use a linear error predictor, and so this can accommodate using counts or binary measurements. And then so the dyadic data is conditionally independent given random effects, but are unconditionally dependent. And so we see here this theta becomes our parameter vector, which is beta x I sub j, and plus the kind of error terms, components of the random effects that we discussed earlier. And then the function g is our inverse link function, so that maps our parameters theta onto our observed outcome y. And then our likelihood function then becomes the likelihood of all of our observations given these parameters becomes the product of the individual likelihoods. And so, for example, if function g is Poisson distributed, then y sub ij is equivalent to a mixed effects Poisson regression model with a log link. So this model allows us to capture second order dependencies, including reciprocity and within actor correlation in these random effects. But the social science literature suggests that there's third order dependencies in a lot of these relationships. And so this includes things like transitivity, balance, and clusterability. And so to account for this, Hoff and Ward incorporate some latent vectors, so latent characteristic vectors, to capture these third order dependencies. And so they define a k-dimensional vector z sub I for each node I. And then so the model response between any two nodes is a function of the similarity of these latent characteristics, and that's represented by the inner product of z sub I and z sub j. And so that expands out our epsilon term to include sender, receiver effect, static error, and the inner product of these latent vectors, which captures those third order dependencies. Note here, so if the vectors z sub I and z sub j have a similar direction, then their inner product will be positive, and then their effect on a third actor, so zi, zk, or zj, zk will be similar to each other. This represents balance and clusterability. These ought to have a transpose in here, but that fell out. Similarly, if both zi, zj, zj, zk are both positive, then the interaction of zi and zk is likely to be positive as well. And so this represents transitivity. And so these are all these third order correlations, third order dependencies that are possible between these actors. And then just to sum up on this inner product term, it's analogous to an error and we can assume that it's distributed about 0. It induces that third order dependence in these relationships, or it captures it rather. And then it allows for additional structure on the moments of epsilon. And so those are listed below. All right, so we're going to talk about how this model is estimated. So first, they're going to reparameterize their model, and they're going to separate their regressors into different chunks, right? And so there's going to be a sender and receiver effects as well as the dyadic effects. And so here, the dyadic effects are captured in this beta sub d x dij term. Si is sender, Ri is receiver. And so we can, and then Zi, Zj is our third order dependence, right? And so they've redefined portions of these, of the X space here to isolate the sending and receiving effects. So then Hoff and Ward are going to, they use Bayesian estimation using conjugate priors and Markov chain Monte Carlo to simulate this model and to get their posterior means for each parameter. And so they construct a Markov chain, and then they sample from the distribution of each of the parameters given the observed outcomes y. And then on the right, we see the algorithm that they use to conduct this MC. And so first they resample the linear effects. So they sample beta D, S, and R, given the rest of the parameters. Then they sample beta S and beta R. And then finally they sample sigma, AB, and sigma gamma from their full conditional distributions. Second, they resample the bilinear effects, and so for each I, they sample Z sub I, which is its latent vector, given Z sub J, where J is not an I, as well as the rest of the parameters. And then finally, they sample sigma Z from its full conditional distribution. And so they're using normal priors here. And then finally, they resample the dyad specific parameters and update their overall theta vector using Metropolis Hastings. And so here they propose the theta vector, it would be theta ij and theta ji, from the proposal distribution given here on the right, which is just from our model. And then they accept it with the probability as put forth by Hastings in his paper. And so essentially this process decomposes the theta sub ij into regressor, sender, receiver, and latent position effects. And then this allows for modeling using various different kinds of distributions in the data, so binomial, Poisson, Gaussian, etc., in the presence of those second and third order dependencies. Okay, so in the paper, Hoff and Ward use this approach to look at interactions in Central Asia from 1989 to 1999. And so at that time, and frankly all the way up to the present, there's been a contentious region with a lot going on. And so there's a few data sets that are available that capture interactions between international actors. And so one of those is the World Event Interaction Survey, and the other is the Conflict on Peace data bank. And so those were both manually compiled. A more recent and advanced, I guess, data set is what used to be called the Kansas Event Data System. It was started at the University of Kansas, um, but has since been kind of absorbed as a government entity. And so I'll address that at the very end. But at the time, it was called the Kansas Event Data System, KEDS. And so this is an automatic encoding of English language news. And so it would scrape English language news off the internet, and then it had an algorithm to encode this in the data set. So a larger and richer data set than the others. And then Hoff and Ward include 106 actors in their model, and so they don't get into the details of why these actors. They piggyback off of someone else's analysis, and these are just kind of commonly accepted significant actors from the period based on other academic literature. And so within this 106, there are 66 countries and 40 non-state actors, and so that Y matrix becomes 106 by 106 sociomatrix of observed outcomes. Okay, and they examine separately conflictual and cooperative interactions, and so those are separate analyses, one of conflict and one of cooperation. And so they determine or scale, I guess, measure the scope of conflict and cooperation based on this Goldstein scale score, which assigns a -10 to extreme conflict and then up to an 8.3 for extreme cooperation. And then so they use that as they detailed earlier, the generalized bilinear model and a Poisson distribution with a log link. They use the Tobler law of geography to define the nearest neighbor and to capture those geographic effects. And so listed below is their model of parameters. And so here, y sub ij given the parameters theta is Poisson distributed. X sub ij is the distance between the countries I and j in thousands of kilometers. And then whether or not I or j are in C is the set of countries. And so the various fixed effects are detailed below here in table 1 for whether one or both of those countries, sender and receiver, are countries. All right, so they run their MCMC simulation with 200,000 iterations, and these are their results. And so figured in the center figure here, this is how they depict their MCMC draws for one particular parameter. In this case, this is the distance effect for cooperation, you see over here on the right. But this shows the kind of this time series plot of their MCMC draws. And so looking at their results, we see that there's a strong distance effect. Notably, it's 30% greater for conflict. And so those are negative signs. So the further apart the countries are, the less likely they are to both have conflict or to cooperate. We show that countries are more likely to share conflict linkages. And we also show that countries are twice as likely to send cooperation than non-countries, but are more likely to receive conflict, which I think stands to reason. The rho value, so that's about 0.8 for conflict and 0.9 for cooperation, indicates a high degree of reciprocity between states, although it's higher in cooperation than in conflict. And then finally, kind of to the crux of their paper, where they want to just discuss these third-order dependencies, they show that there's a large degree of sender and receiver specific variance as well as third order dependence. So you can show that because sigma A squared, sigma B squared, and sigma Z transpose Z squared are all greater than sigma gamma squared. And then it's important to remember that the standard empirical approaches used in most international relations literature and perhaps political science more broadly assume that these kind of effects are in effect zero when they're excluded from most simplified models. All right, so here we're going to kind of look at the performance of the model. And so we find that the bilinear effects model is fairly accurate in terms of prediction. They show that the inclusion of their latent variables improves the fit of their regression. And then they can show that there's an improvement in the prediction of values. So from 0.75 to 0.85 correlation between the actual and predicted values. And so they do this by using resampling methods to assess the out of sample predictive power, right? And so those effects are shown, the out of sample prediction effects values are shown here in table 3. And so they show the out of sample prediction power or correlation, right? Whether they simply look at fixed effects, include random intercepts, or whether they also include the latent positions. And then we can show, and they do it both on a normal scale and on a log scale. And they show that particularly when looking at it on a linear scale, the ability of the full model to accurately predict outcomes is significantly higher. Here in the center, Hoff and Ward have plotted the posterior means of the actor random effects for conflict. And they note that the effects for cooperation are similarly distributed and similarly ranked. So on the top panel, there's sender random effects, and the bottom is receiver random effects. And so I pasted in the flags or symbols of the top handful of actors here on the ones that have the highest random effect for sending conflict and the highest random effect or like actor specific effect for receiving conflict. And we'll see they're similar. And so for senders, we see the top is the United States, followed by Ukraine, the United Nations, Iran, and Afghanistan. And then for receiving, we have Ukraine, the U.S., Afghanistan, the United Nations, and Iran. And so we kind of see here is the UN and the United States during this period doing a lot of kind of world policing, and then the Ukraine, Iran, and Afghanistan kind of being at the center of various conflicting actions, various international contentions, which stands up to the common sense test, I suppose. On the right, Hoff and Ward have plotted their latent positions using their latent vectors Z. So the two like elements of that it's a 2x1 vector for the Z vectors, and so they plotted the two components of that against each other, and then put each actor So the nodes are I, each node I on this coordinate plane. And so what we see is that there's significant clustering based on these latent characteristics between unmeasured, unobserved latent characteristics among these various actors. And so over here on the far left, there's a lot of actors that are involved in the Armenia-Azerbaijan conflict, kind of closer to the center. There are various actors involved in the Kosovo conflict. And then on the bottom right, there's multiple actors that were involved in the Afghan-Pakistan, were involved with Afghanistan and Pakistan during the same time period. And this paper was written in 2004, so conflict in Central Asia, particularly in Afghanistan, was a hot topic at the time. And so if we blow out this section on the bottom right, we can look at kind of a little more detailed view of the clustering, and then here they've highlighted 3 actors within these clusters. One being Osama bin Laden, the leader of Al Qaeda. One being the nation of Saudi Arabia, and the other is Abdul Rashid Dostum, who is the leader of the Northern Alliance during the civil war in Afghanistan and the U.S. invasion. So these latent variables are kind of, I think, fundamentally hard to interpret, but it's interesting to see that they've clustered like this into these various camps aligned with different conflicts in Central Asia. And so finally, the conclusion. And so Hoff and Ward showed that this model provides a generalizable way to account for second, third order dependencies in regression models for dyadic data. So while most current analyses in political science, and especially those in international relations, ignore these effects, but this is a method to incorporate them. They show that latent space variables are useful to capture interdependencies and then allow mapping and prediction of unmeasured relationships. And then finally, a variety of discrete and continuous processes can be adapted to this model based on their data generating processes. And then finally, the 2 references here. One is the paper itself, so modeling dependencies in international relations networks. And the other is the Kansas Event Data System. So that has been kind of taken over, subsumed by the U.S. federal government. And so that's now called the Computational Event Data System. And you can find that at the URL below. All right. I hope this presentation was clear. Feel free to contact me with any questions, and have a wonderful day.